If you consider the characterization of the rational function field in terms of its genus and containing degree divisor, and thanks to Riemann-Roch theorem, first we will be able to observe that all A spaces of given any divisor A, if its degree is negative. From the general theory, we know that it is a trivial space and is of dimension 0. And if degree is bigger than or equal to 0, in this case, since the degree is equal to 2g minus 2 and genus is 0, we can compute the dimension as degree plus 1 minus g. And for all spaces, indeed, we will be able to compute its dimension. For instance, as we have considered before, if you consider the divisor np infinity, here p infinity denotes the pole of x, and in this case, directly we can say that it has dimension n plus 1, and the elements from the x powers, the powers up to m, forms a basis. And similarly, for any degree m divisor, which is determined by the 0 of x in this case, again is of dimension n plus 1. And in this case, we can observe that these elements in this forms a basis for this L space. And we have characterized the canonical divisors depending on their dimension and degree. So that means if they have dimension g and the degree 2g minus 2. And if we are wondering about how does the canonical divisors look like in the algebraic function field, it will be enough to consider degree 2g minus 2 divisor. It's going to be always degree minus 2 as genus is 0. And since they are always negative divisors, their dimension will be 0. And often in the theory we consider, we work with this canonical divisor for the rational function fields, but we also know that for another canonical divisor, for instance, for 2px, here px denotes the 0 of the x, we know that they are equivalent. And for instance, in these two examples, we can see that their equivalence is determined by the function x squared. And in the rational function field, if you consider two divisors which are equivalent to each other, in general theory, indeed, I mean, in any algebraic function field, we know that equivalent divisors, they have the same degree. But in this case, we will be also observe that if they have the same degree, they're also equivalent. And to see this equivalent, it will be enough to prove the sufficient condition. So that means if you consider two divisors, they're of the same degree. In this case, if we work with a divisor b minus a, since it has degree 0, I the assumption, and this is bigger than or equal to 2g minus 2. It has dimension degree b minus a plus 1 minus g. And we know that genus is 0, degree is 0, this is 0. So for degree 0 divisors, which has dimension, I am sorry, this is going to be 1, because this is degree 0. For the divisors which has degree 0 and is of dimension 1, we know that they are principal. And this shows the equivalence. In the, one of your homework question, you will see that every degree 0 divisor is principal. But in the rational function fields, however, later we will give a counterexample. It doesn't work in general. But for the moment, thanks to this observation, we can also see that the class group of the rational function field is isomorphic to Z. Again, if you consider the homomorphism between the divisor group and Z. So the degree 0 divisors, in this case, if you look at the kernel of this group homomorphism, so in this case, degree 0 divisors will be the principal divisors. And takes the first isomorphism theorem, we can see this isomorphism. And finally, thanks to this observation, this every degree 0 divisor is principal. In general, we are able to, in some sense, represent the basis of all Riemann-Roch spaces of all divisors. In other words, for given divisor in the rational function field which has positive degree, we know that its dimension can be computed to its degree plus 1, and thanks to, if you consider, okay, let me write, it has degree m, which is bigger than or equal to 0, then we can observe that indeed any degree m0 divisor is equivalent to divisor mp infinity. Here again, p infinity is the pole divisor of x, because thanks to this observation in item 3, we know that if they have the same degree, they are equivalent to each other. And thanks to this equivalence, we know the existence of a function that which allows us to write the divisor mp infinity as the divisor a plus the principal divisor z. And we can identify an isomorphism between these two S spaces by mapping the functions x to x times z. And this gives us the vector space isomorphism And we have also observed that its inverse is determined by the multiplication by Z inverse. And thanks to this isomorphism, if we want to represent a basis of any L space, it will be enough to consider the basis of the NP infinity and to check their images under this isomorphism. And these images gives us a basis for the degree A, for the dimension of the degree M divisor A.